In this video, we are going to go through 5 of the most common advanced stoichiometry problems: limiting reactant and percent yield, combustion analysis, gas problems, solution problems with titrations, and hydrate analysis. Let's get started. Question 1. In a lab, 28.5 grams of iron is reacted with 48 grams of chlorine to produce iron 3 chloride. If the reaction only has a 78.5% yield, what mass of iron 3 chloride is actually produced? The equation is given. When we are given amounts for both reactants, it is a limiting reactant problem. The goal will be to convert both reactants to the same unit in the same product to see which reactant makes the smaller amount of product. The reactant that makes the smaller amount of product will be the limiting reactant. The product amount found that is smaller will be the maximum amount of product that can be made and will also be called the theoretical yield. Theoretical yield is the amount of a product we are expected to make without any errors from lab. They also gave us the percent yield. The percent yield was found from the actual yield and the theoretical yield. The percent yield equation is actual yield divided by theoretical yield times 100. We will first want to find the limiting reactant by converting each reactant to grams of iron 3 chloride. At the same time, when we find the smaller amount of iron 3 chloride made, this will also be called the theoretical yield to use for the percent yield equation. We can then find the actual yield for the answer. First, we will convert both 28.5 grams of iron and 48 grams of chlorine to grams of iron 3 chloride to find the limiting reactant and the theoretical yield. These will both be grams to grams conversions. We first convert from grams of the first compound to moles of the first compound using the molar mass of the first compound. Then we will convert from moles of the first compound to moles of the second compound using the mole-to-mole ratio from the balanced chemical equation. We can then convert from moles of the second compound to grams of the second compound using the molar mass of the second compound. For iron, the molar mass will be 55.845 grams per mole. The mole ratio will be 2 moles of iron 3 chloride over 2 moles of iron, and the molar mass of iron 3 chloride will be 162.195 grams per mole. We start with 28.5 grams of iron over 1. In the next fraction, 55.845 grams of iron goes on the bottom and 1 mole of iron on the top. In the next fraction, 2 moles of iron goes on the bottom and 2 moles of iron 3 chloride on the top. In the next fraction, 1 mole of iron 3 chloride goes on the bottom and 162.195 grams of iron 3 chloride on the top. Grams of iron cancel out, moles of iron cancel out, and moles of iron 3 chloride cancel out. We are left with grams of iron 3 chloride. Calculating, we get 82.8 grams of iron 3 chloride. This is not our answer yet for the theoretical yield of iron 3 chloride. We have to compare this number to how much can be made from grams of chlorine. The smaller amount of iron 3 chloride will be the theoretical yield for iron 3 chloride. For chlorine, the molar mass will be 70.9 grams of chlorine per mole. The mole ratio will be 2 moles of iron 3 chloride over 3 moles of chlorine, and the molar mass of iron 3 chloride will be 162.195 grams per mole. We start with 48 grams of chlorine over 1. In the next fraction, 70.9 grams of chlorine goes on the bottom and 1 mole of chlorine on the top. In the next fraction, 3 moles of chlorine goes on the bottom and 2 moles of iron 3 chloride on the top. In the next fraction, 1 mole of iron 3 chloride goes on the bottom and 162.195 grams of iron 3 chloride on the top. Grams of chlorine cancel out, moles of chlorine cancel out, and moles of iron 3 chloride cancel out. We are left with grams of iron 3 chloride. Calculating, we get 73.2 grams of iron 3 chloride. Comparing both values found, 73.2 grams of iron 3 chloride is the smaller amount of product made. This value will be our theoretical yield, and chlorine is the limiting reactant. Next, we can find the actual yield of iron 3 chloride using the percent yield given and the percent yield equation. 78.5% equals X divided by 73.2 grams times 100. Rearranging the equation and solving, we get an actual yield of 57.5 grams of iron 3 chloride. Question 2. The combustion of 1.5 grams of an unknown hydrocarbon A compound containing only carbon and hydrogen produces 4.71 grams of carbon dioxide and 1.93 grams of water. What is the empirical formula of the hydrocarbon? This is a combustion analysis problem where we use the grams of carbon dioxide and the grams of water to find the moles of carbon and the moles of hydrogen needed to find the empirical formula for the hydrocarbon. To find the empirical formula for a combustion analysis, we need to first convert grams of CO2 to moles of CO2, and then moles of carbon, and grams of H2O to moles of H2O, and then moles of H. Next, we will divide each value by the smallest mole value found to find the whole number ratios needed for the empirical formula. Let's start with our steps to find the empirical formula from the grams of CO2 and the grams of H2O given. To convert grams of CO2 to moles of carbon, we will use the molar mass to first convert to moles of CO2, and then we will use a mole ratio to convert from moles of CO2 to moles of C. The molar mass for CO2 will be 44.011 grams of CO2 for every 1 mole of CO2. The mole ratio will be 1 mole of carbon for every 1 mole of CO2. Setting up all units to cancel, we start with 4.71 grams of CO2 over 1. In the next fraction, 44.011 grams of CO2 goes on the bottom and 1 mole of CO2 on the top. In the next fraction, 1 mole of CO2 goes on the bottom and 1 mole of carbon on the top. All units cancel and we are left with moles of carbon, and we get 0.107 moles of carbon. To convert grams of H2O to moles of hydrogen, we will use the molar mass to convert to moles of H2O, and then we will use a mole ratio to convert from moles of H2O to moles of hydrogen. The molar mass for H2O will be 18.016 grams of H2O for every 1 mole of H2O. The mole ratio will be 2 moles of hydrogen for every 1 mole of H2O. Setting up all units to cancel, we start with 1.93 grams of H2O over 1. In the next fraction, 18.016 grams of H2O goes on the bottom and 1 mole of H2O on the top. In the next fraction, 1 mole of H2O goes on the bottom and 2 moles of hydrogen on the top. All units cancel and we are left with moles of hydrogen, and we get 0.214 moles of hydrogen. We were also given the total amount in grams for the hydrocarbon. To double check our work, we can convert both mole amounts found for carbon and hydrogen to grams to see if the total will be equal to 1.50 grams. Multiplying each mole amount by the individual element's molar masses, we get about 1.285 grams of carbon and 0.215 grams of hydrogen. Adding these values together, we get 1.50 grams total. This confirms we are solving the question correctly, and we can continue to the next step to find the empirical formula. Next, we divide each value by the lowest amount of moles found. The lowest mole amount will come from moles of carbon, so we will divide each value by moles of carbon. After dividing, we get 1 carbon and 2 hydrogens. The empirical formula will be CH2. Question 3. Ammonia reacts with oxygen to produce nitrogen monoxide and water. If 10 liters of NH3 gas at 300 Kelvin and 1.5 atm is reacted with excess oxygen, what volume of NO gas will be produced if it is collected at 350 Kelvin and 2 atm? Gas stoichiometry will have stoichiometry and ideal gas law calculations. For stoichiometry, we will be using grams to moles conversions, using the molar mass and mole ratios from the balanced equation. And for ideal gas law calculations, we will be using volume, temperature, pressure, and moles for one of the compounds in the reaction to solve for a missing variable. We have to be careful to match the correct compound with the variables given for the ideal gas law. We can organize the information first. For NH3, we were given a volume of 10 liters, a temperature of 300 Kelvin, and a pressure of 1.5 atm. We are only missing moles for the ideal gas law. Already we should be thinking that we can solve for moles of NH3 first, using the ideal gas law because we are only missing one variable needed for the calculation. For the ideal gas law equation, we need pressure, volume, moles, and temperature. We were given pressure, volume, and temperature, so we are only missing one variable, moles. For NO, we want to find volume. We have a temperature of 350 Kelvin and a pressure of 2 atm. We also need moles for the ideal gas law equation for NO. For NO, We are missing two variables for the ideal gas law calculation, so we should start with NH3 first. If we find moles of NH3 first using the ideal gas law, we can then convert from moles of NH3 to moles of NO using stoichiometry, and then use moles of NO in the ideal gas law equation to solve for the volume of NO. To find moles of NH3, we will use the ideal gas law, PV equals nRT. We are given a pressure of 1.5 atm, a volume of 10 liters. We are solving for moles. The ideal gas constant R is 0.08206, and the temperature is 300 Kelvin. Solving, we get 0.61 moles of NH3. Next, we can convert from moles of NH3 to moles of NO, using the mole ratio from the balanced chemical equation. There is a 4 in front of NH3 in the equation, and a 4 in front of NO, so the mole ratio will be 4 moles of NH3 over 4 moles of NO. Setting up units to cancel, we start with 0.61 moles of NH3 over 1. In the next fraction, 4 moles of NH3 goes on the bottom, and 4 moles of NO goes on the top. Moles of NH3 cancel out, and we are left with moles of NO. Solving, we get 0.61 moles of NO. We now have moles of NO, so we can use the ideal gas law equation to solve for the volume of NO. We have a pressure of 2 atmospheres. We are solving for volume. We have 0.61 moles. The ideal gas constant is 0.08206, and the temperature is 350 Kelvin. Solving, we get a volume of 8.8 liters of NO. Question 4. It takes 32.50 milliliters of a 0.750 molar sodium hydroxide solution to completely neutralize a 25 milliliter sample of phosphoric acid. What is the molarity of the phosphoric acid solution? When we are using molarity values in problems, we can think of these values as conversion factors to convert between moles and liters for that specific compound. For example, we are given 0.750 molar sodium hydroxide, and we can think of this value as 0.750 moles of sodium hydroxide over 1 liter of sodium hydroxide. We can now convert between liters of sodium hydroxide and moles of sodium hydroxide using this value. We should also notice that we are given the volume and molarity for sodium hydroxide. For molarity conversions, we have 3 variables: molarity, volume, and moles that fit together in the equation molarity equals moles divided by liters. If we have 2 out of the 3, we could find the missing variable first. The missing variable this time is moles of sodium hydroxide, so our first step could be solving for moles of sodium hydroxide using the volume and the molarity. The volume given is 32.5 milliliters of sodium hydroxide. We can convert milliliters to liters using a prefix conversion, and then liters to moles of sodium hydroxide using the molarity value. We need to find the molarity of the phosphoric acid solution. Molarity equals moles of solute divided by liters of solvent. We are given the volume of the phosphoric acid solution, so we are only missing moles. We will have to find moles of phosphoric acid and liters of phosphoric acid. Our first step is converting to moles of sodium hydroxide. We can add on to this conversion and convert to moles of phosphoric acid using the mole-to-mole ratio from the balanced chemical equation. Once we have moles of phosphoric acid, we will need to convert 25 milliliters to liters to then solve for the molarity of phosphoric acid by dividing moles and liters. Let's first start with finding moles of phosphoric acid. For our conversion factors, the prefix conversion to convert from milliliters of sodium hydroxide to liters of sodium hydroxide is 1,000 milliliters over 1 liter. To convert from liters to moles of sodium hydroxide, we can use the molarity value, 0.750 moles of sodium hydroxide over 1 liter of sodium hydroxide. To convert from moles of sodium hydroxide to moles of phosphoric acid, we can use the mole ratio from the balanced equation, 3 moles of sodium hydroxide over 1 mole of phosphoric acid. Setting up units to cancel, we start with 32.5 milliliters of sodium hydroxide over 1. In the next fraction, 1,000 milliliters of sodium hydroxide goes on the bottom and 1 liter of sodium hydroxide on the top. In the next fraction, 1 liter of sodium hydroxide goes on the bottom and 0.750 moles of sodium hydroxide on the top. In the next fraction, 3 moles of sodium hydroxide goes on the bottom and 1 mole of phosphoric acid on the top. Milliliters cancel out, Liters cancel out, moles of sodium hydroxide cancel out, and we are left with moles of phosphoric acid. Solving, we get 0.008125 moles of phosphoric acid. Next, we can find the liters of phosphoric acid. We have 25 milliliters of phosphoric acid. We can divide by 1,000 to get 0.025 liters of phosphoric acid. In the last step, we can solve for the molarity of phosphoric acid by dividing the moles of phosphoric acid by the liters of phosphoric acid found. Dividing, we get 0.325 molar phosphoric acid. An alternative way to solve will be to use the acid-base neutralization equation, MAVA over A equals MBVB over B. MA is the molarity of the acid, VA is the volume of the acid, A is the acid coefficient in the equation, MB is the molarity of the base, VB is the volume of the base, and B is the base coefficient in the equation. We are solving for MA. The volume of acid is 25 milliliters, the acid coefficient is 1, the molarity of the base is 0.750 molar, the volume of the base is 32.50 milliliters, and the base coefficient is 3. X times 25 divided by 1 equals 0.750 times 32.5 divided by 3. Solving, we get the same molarity for H3PO4 as the previous calculation, 0.325 molar. Question 5. A 2.5 gram sample of a hydrated salt of copper 2-sulfate is heated until all the water is driven off. The remaining anhydrous CuSO4 has a mass of 1.598 grams. What is the value of X in the hydrates formula? To solve for the hydrate formula and the unknown amount of water present in the hydrate, we have to first find the grams of copper 2-sulfate and the grams of water separately, convert to moles of copper 2-sulfate and moles of water, and then divide each by the lowest mole amount found to find the whole number X value for the hydrate formula for H2O. First, we are going to find grams of copper 2-sulfate and grams of water separately. We were given a total hydrate sample equal to 2.5 grams. Grams of copper 2-sulfate and grams of water equal 2.5 grams. We were told that copper 2-sulfate has a mass of 1.598 grams, so setting grams of H2O equal to X, we get grams of water equals 0.902 grams. Next, we are going to convert grams of copper 2-sulfate and grams of water to moles by dividing each by their molar masses. We get 0.010012 moles of copper 2-sulfate and 0.05006 moles of water. Next, we can find the whole number ratio for water by dividing each mole value by the lowest mole amount. The lowest mole amount found was 0.010012. Dividing each by that value, we get 1 copper 2-sulfate and 5 waters. The hydrate formula will have a 5 in front of H2O.